Okay, the light is green, which is the sign that we can start. So it's my pleasure to introduce our speaker today, Christophe Eloy. He's been a friend for many, many years. He's a professor and researcher in France, at Centrale, Marseille, and École. What can I tell you about him? He's a graduate of École in France, and he did a PhD. He used to be a high Reynolds numbers instability and rotating flow person, and he's no longer that person. He now works a lot on problems in biomechanics. He's interested in mechanics and cooperation and evolution and natural selection. So he works on fish, he works on, I'll tell you about trees. He continues to work on classical solid and fluid mechanics problem, but he switched from purely physical to mainly biological problems. So today we'll tell you about his work on trees.
Thank you, Eric. So yeah, I'm going to talk about this thing I did on trees. That started when I was editing Eric when he was back in UCSD. And it really started as a side project, curiosity-driven. And well, you see that it's a nice story about it. So we all know what a tree looks like. This is a node. What is interesting in this shape is that there are many, many different scales. So here we are only looking even at the macro scale. There is a tenfold, even more difference between the size of the trunk and the size of the small twigs that are here. But the trunk started with this diameter it was just a sprout. And so the question is, how does this hierarchy of length, how this self-similar structure, we show later, it's often self-similar, how does it grow into this shape? It's not the shape in the sense of a circle or a square. It's more the self-similarity and the characteristic of self-similarity of these shapes that I'm interested in. And it's not at all obvious that it grows into this self-similar shapes. Okay, so let's talk about it. So to quantify self-similarity, we use a fractal dimension. And to calculate fractal dimension, I will only consider the length of different branches, not the diameter yet. And for when you construct a very simple regular tree like this, the fractal dimension is directly linked to the ratio between the length of two successive segments. And this is the formula. So K is the rank, and L is the length, and N in this case is 2. It's the number of daughter branches per mother branch. And so when this ratio is, in this case, square root of 2, you fill the space. When you have a fractal dimension of 2, when it's less, there is mainly void, and you can define fractal dimension this way.
The number of daughter branches is the same for all these.
Yes, it's always one branch divided in 2, that divides in 2, that divides in 2.
Right, so something else is different.
Length.
Yes, of course.
Yeah,
the ratio of length.
The ratio of length is different. That's the only difference in this picture.
The ratio of the total length in that generation.
Yeah, but it's the ratio between. In this case, it's the ratio between. Check the pointer. This is the ratio between this length and this length.
That's not one.
No, it's not 1. It's 2. It's square root of 2.
But you said D is 1, so the formula doesn't change.
Yeah, there's only one.
So that's 2. That's 2. There's a factor of 2 here, and here is a factor of square root of 2. N is 2. N is the number of daughters for each mother branch. Yeah, because here it's 2, but for each branch there could be 3, 4, 5 ramifications. N is this number. Okay. So the usual way to measure this fractal dimension from an experimental point of view is using box counting methods. Well, surprisingly or not surprisingly, it has not been done many times with real trees, because they are very big and it's very hard to do, and there are thousands of branches, and so there are very few measurements. The only 2 measurements that are on trees give fractal dimension around 2, and then there have been some measurements on the leaves, on the foliage, on the tree crown, and when you expect the fractal dimension of the foliage and the structure that support the foliage to be the same, except for very peculiar structure. So we expect that we get something similar. And so there is this paper, for instance, that shows that for 10 different species, the average fractal dimension you find is around 2.5. So contrarily to lumps, for instance, or the arterial system, where there is a reason to be volume filling, to have in every part of the volume a vein, or in a tree, it's not volume filling, there is many voids. And so that was for the length. But there is also an interesting observation by Leonardo about the diameters of the branches. So what he observed is that, that's this drawing, that when you take a tree, the cross-section of a trunk is the same as the cross-section of the total cross-section of these two branches, and the same as the cross-section of the sum of these two branches, these 4 branches, and so on. So when you fold the tree as an umbrella, the cross-section remains constant along the height. And for this measurement, one way to quantify it is to take every single branching node in the system and to fit an exponent. So if this exponent delta is 2, then you have conservation of cross-section, and for arteries or for the airways, the exponent is closer to 3, for instance. So that's one way to quantify the diameters. How the diameters vary in this branching structure. So again, there have been very few measurements. Here is an illustration. So this is it looks more like a tree than these two. This looks more like a arterial tree or lungs. And this, I don't know any example of this kind of scaling. So there have been very few measurements. So Mandelbrot himself took data from McMahon and Kroner in this 70s paper, and he said that the data will correspond to an exponent that is slightly smaller than 2. And then there have been these 4 measurements. So this is an undergrad paper. This is the paper on 1 species and a few individuals. And recently there has been a larger study on different species, and you find an average that is indeed around 2. So the other reason, well, it's not a reason, but another observation is that people doing computer graphics, it's not a computer graphic tree, but people doing computer graphics use this rule to have diameters that look natural, let's say.
That's a question.
Yes.
So the diameter remains constant before the branching. The diameter doesn't
Not
change.
really, but yeah, depends where you measure it. But, yeah.
Roughly constant.
Yes. Well, it all depends on the species, but let's say that for every branching, you take it just below and just above. Not too close to the node, because then it's not precisely defined. But no, they do it experimentally. It's a good question. Okay, so this was for sort of very irregular structures, but in the retriever is more randomness, and in particular it's not symmetric and it's not regular, so it's not a fractal in this sense. But you can define, or you would like to define an average ratio of length between 2 levels in the hierarchy and an average ratio of diameters. And this average of the ratio of lengths is linked to the fractal dimension, n being again equal to 2 in this example. It's the number of daughters for one mother. And you have a similar formula for the Leonardo exponent for the diameters. So in general, Leonardo exponent is close to 2, and the fractal dimension is somewhere between 2 and 3. So these 2 exponents are not equal, which means that the length and the diameter do not vary in the same fashion. So it's not self-similar in this sense. So when you zoom in the picture, it's not the same picture as the whole. It's called self-affine. But it's just a vocabulary thing. So the question is, how do you define the rank in a structure that is not regular anymore? And the way to
Christophe,
this.
in what dimensional space you're doing this? Because I think the
Three.
answer is
Yes.
your previous drawings were in 2 dimensions.
Yes.
So you're shifting. Yeah, okay.
The
so now
dimension
you-
is not important when you take this definition.
Well, it's important because it's either between 2 or 3 or 1 and 2.
Oh yeah, of course. Yeah, yeah. This argument is because 3 would be volume filling. You don't expect anything bigger than 3, otherwise you would have crossing and overlaps. 2 would be what you get if the foliage is a sphere, for instance, or a surface, and there is no leaves inside this. Then you expect a structure that is of dimension 2. And so you expect something in between these two things, because generally the foliage is not smooth. There is some roughness or some fractality to it. So it's somewhere in between. And there is some roughness, both because it's irregular and because there is some transparency in the foliage. But we will see that it's important. Okay. So the question is, how do you define the rank in an arbitrary structure that's not regular? And one way to do it is to use what people do when they study river networks. So it's the same problem. How do you number the different rivers in a river network? And the way it is done is that you give rank 1 to the final branches. And when 2 of these branches meet, they form a branch of rank 2. And when any branch meet another, if their rank is the same, they end up forming a branch of the rank that is +1. But if the rank is different, for instance here, the green one remains green because the blue one has a rank that is less than the green one. So you end up having, you can have, not in this particular example, but you can have very long branches of a succession with the same number to them. And so when you do that in a tree, not this one, but a real one, this is data from Leopold in 71. So there are 2 trees here, a pine and a fir. So what is plotted here is as a function of the rank, it's the number of branches. So for the terminal branches, you see that there are 500 ones, and the trunk there is only 1, and their mean length. So it goes, it's in feet, I think. So it's go from half a foot to about 20 feet for a trunk. Yes.
Sorry, Christophe, how do you rank them? Like when I see the yellow trunk, right?
Yeah, you start by you don't start by this one. You start by the extremities.
Okay.
So let's say that all the extremities are numbered 1.
Oh, okay.
That's one way
But
to
I'm
do it.
looking at, oh, okay.
And when 2 extremities meet, it's not an extremity anymore. So if you remove all the branches of rank 1, then what remains are new extremities that have the rank 2, and so on. You do that iteratively. That's another way to say it.
So when 2 big branches join, can they be off by more than 1 rank?
Yeah, they can be off by. There could be a very small branch here, and so you'll have a branch of rank 1 meeting the trunk, which is of
I
rank
see,
6
okay.
here. And that's a good way to do it, because you don't want the rank to change just because there is a very small branch on the trunk. You know,
Then
it's still the
my
trunk.
argument
So.
would be the other way around then. The big trunk would be rank 1 and then rank 2.
Yeah, well, you can reverse the ranking if you want it to be rank 1, but the other way that is done is to go from the ground. Then you have to give some.
No, it's best to come in from the
There has to
outside.
be a criterion to tell you which one is which when you split.
I see.
Is it 2 new ones or is it the same one continuing? So this is one way to do it. Yeah. Well, there are other ways to number branches. This is a topological one. It is both simple and that gives good results in terms of these curves. But there are alternative ways for sure. So it's good here because you see that when you do this numbering, you have the geometrical progressions, both of the number of branches and their mean length, which is the signature of self-similarity.
Can you rank
and so-
their shadows the same way?
What?
Just kidding.
Oh yeah.
Nice
Yeah.
shadow.
And so through these slopes, you can also define a fractal dimension, which is exactly the same as the one before. Just that you can do it for any structure here. You don't need to be regular. Okay, so why are 3 self-similar? So you have to keep in mind that the tree is the result of a growth. And the growth is embedded in the structure itself because of the annual rings. And this is a spectacular work by the sculptor Giuseppe Pennon. So what he did is that he bought one of the cedar that fell down during the 99 storm in France. This was one of the cedar that was planted on the order of Marie Antoinette. And this cedar, he sculpted a window, and then he followed one of the rings, one of the annual rings. So inside the 250-year-old cedar, you can see its shape when it was only maybe 20 years old. As Marie Antoinette probably saw it. So it's very spectacular. So he did it several times. So this is, you see that it's not exactly the same one. And there is another one. Here you see him working on it. And so what is important here is that when you have a big trunk like this, when you go back in history, you see that it is made of smaller segments. It used to be an assembly of smaller segments. And so in order to get a very long trunk or very long branch, you need to assemble small segments, but you need also to shed the branches that are on the side. So in order to get self-similarity, not only you need to grow, but you need also to remove material in some sense. And in case you don't know, trees, wood cannot grow in length, it can only grow in diameter once it's wood. So the only way to get a longer branch is to assemble end-to-end several branches. So usually the explanation that is given is an explanation related to the transport of sap. So what people say is that if you imagine that every leaf is connected by a pipe or a given number of pipes to the root system, then at each branching node, the number of pipes is conserved by construction. So if the cross-section is proportional to the number of pipes, then the cross-section is also conserved at each branching node. So you recover Leonardo's rule. But when you look at which part of a trunk or a big branch is devoted to transport, for instance, this is the trunk of an oak, only the sapwood, so the wood that is lighter here, is biology alive and transports water. The hardwood that is inside is dead from a biological point of view and is only there for mechanical support. So the explanation doesn't tell you what this part is for. And the portion that is devoted to transport can be very different depending on the species and depending on the climate. And oaks do that, and many species in our climates do that, because in winter the climate can be very cold, and so the water freezes. So you need to build new vessels every year because you cannot use the vessels in which the water has been frozen. And so this is one explanation, and there is another explanation that I will try to convince you is not completely stupid, I guess. It's called, it's a long word, so it's phygmomorphogenesis. What it says is that every plant can respond to mechanical stimuli. So when you take a plant, and this is a model plant for botanists, Arabidopsis thaliana, when you take a plant, so this is a control experiment, and this is an experiment where the experimentalist every morning touches the plant 80 times. So it's a caress to the, and it changes completely the growth.
Touches where?
It doesn't say. I think it's just it's like caressing a puppy. So what's interesting is that the growth is completely different apparently, but when you weight every single plant, the weight is the same. So, well, for short time at least. So what happens is that photosynthesis is the same, so you produce the same amount of sugars, but the allocation of this biomass that is produced is completely different. So in this case, biomass is allocated to roots and to have slightly thicker stems, but the amount of biomass is the same, so it just responds that triggers different allocations.
Presumably,
Yes.
the rubbing must be upward.
Which one?
The stroking, is it upward?
No, it's just
Rushing across the top.
you could do you could just check the many different ways, but it's just as long as you don't cut it.
It's a well-adapted evolutionary response.
It's a response to apparently it's a response to the strain, to the mechanical strain.
If you get brushed every morning by an animal passing by, you don't want to be tall and thin. I mean, it's an evolved response to, it's appropriate. And if no one ever comes near you, you may as well, be spindly and.
Sorry, I got confused. I
Yeah,
thought
it's the other way
it was
around.
the way around.
Yeah.
Yeah, this one
Yeah, the other way around would be spindly.
Sorry.
So the question is, if you apply the same principle to big structure, to trees, what does it look like? Well, it's hard to tell, but there are examples where this phenomenon may be involved. This is, for instance, the same tree species, Jeffrey pine, growing in very different conditions. You see that the shape can be very different. But here, it's not only thick morphogenesis; it's also because these very windy conditions, the branches are being shed and probably different things occurring, but it's still a nice picture. So the question is, if you take into account this response to mechanical sensing, what sort of architecture do you get? And if you want to, if you imagine your tree for a minute, what is the best response in order to be able to resist wind? That's the question I'm asking. And to start with, we'll do it with a very simple model. So let's assume a regular fractal tree. So this time n is 3. That's the number of daughter is 3 here. That's the same definition. So let's say the ratio here is constant and the angles are constant. And to make even things simpler, we'll consider that all branches are in the same direction. And there is wind blowing on this structure, and you ask yourself, what should be the diameter of every branch such that this structure is optimal to resist wind?
So this is embedded in a two-dimensional plane.
It can be anything, because the only assumption here is that the force given by the wind is, no, let's say it's two-dimensional, okay. But it still has a diameter. So
I understand, but
it's in a plane.
the axis.
Yeah, it grows in a plane, for simplicity. Also did it with angles and so
I'm
on.
asking because your drawings are planar, but you write in fractal dimension between 2 and 3.
Yeah, it doesn't matter. Here you can have overlap. I can draw whatever I want. I can draw something of fractal dimension 10 if I want, but it's not physical.
This
But,
is just
It's a
projected.
combinatoric thing, isn't it? You're just talking about a graph here, with no notion of dimension.
okay, no, let's put it in a different way. Let's say I have a three-dimensional structure, but I will assume for now,
Oh, sure, yeah.
but I'm ignoring any particular angle between every single branch and the wind. I'm assuming that for simplicity that this angle is always 90 degrees. And yeah, let's just put it this way. So the question is, what should be the diameters? And another way to say it is that what should be the ratio of diameters between two ranks? And without any knowledge, this ratio could depend on the rank. It could be different for the branches that are near the trunk or the branches that are near the top. And an interesting thing is that there is a parallel between this discrete problem and a continuous problem of a cantilever beam. And it's a beam where the thickness varies with the height and the width also varies with the height, such that the thickness is related to the diameter. And if you cut this beam such that you have here pieces that are almost square, then you recover something like this. And so here you have 9 branches, and here 3, and here 4. And you can cut through these planes because there is no mechanical stress in this plane when you apply a force in this direction. And so the question is, what should be the Leonardo exponent in this case?
Are you keeping, sorry, can I ask? Are you keeping the whole volume constant?
No, not necessarily. No. The argument here yeah, maybe I should tell you right now, but the argument here is that you're optimal when you are at the limit of fracture everywhere at the same time. And it's optimal because if you reinforce any part of the tree, it's useless because it will break down anyway. So you want to be at the verge of fracture everywhere at the same time for a given wind. So we want to calculate that. So there is a parallel here. So I can go a little faster, but you understood the principle. Here it's the diameter. Here it's the diameter times the number of branches. So there is a parallel between this discrete system and this continuous system. And so the fractal dimension actually gives you this formula that the ratio between the thickness and the width is related to the S is the distance from the top, and it's related to a fractal dimension. So the question is, what is H, or what is the Leonardo exponent such that it is optimal?
No, can you define your optimality again? I couldn't quite follow that. And I'm
Yeah,
not
it's
sure I agree also.
You may disagree, but
Okay, what's your
my argument is that you are optimal when let's imagine you have a fracture for a given stress. You're optimal when this stress is reached for a given wind everywhere in the structure. You have the same stress.
For the tree. You would think when the wind, if you see a storm, usually there's some small branches cut off, and that saves the tree. So you want to actually have some.
Depends on the wind.
Well, I understand,
Sometimes
but from a what's a survival point of view for the tree.
Yeah.
Wouldn't you actually want to design some vulnerable part so that they can be broken off?
So yeah, it would be
That'd be
clever.
another-
It would be clever. So let's say for now that I didn't think about it. So I only thought about having constant stress, and then I show you at the end that your idea is clever, but that's not
That's
optimal.
not what they do.
No, it's
It's
not
not
optimal.
what works in democracy, right?
It's not optimal.
So I think your assumption is reasonable because the tree want to be like every part to be safe up to some threshold.
No, but it's not. It's clever because the trunk the trunk of its branches are far more important than the small ones, because when this one falls down, these don't survive anyway. So the small ones need the big ones, but not the other way around. So it makes sense. But you see that if it is present, it's very small. The stress is almost constant.
I'm still a little confused what you're optimizing.
I'm not optimizing. I'm trying to find what should be the thickness of this, beam in order to have a constant stress when I apply a force like wind, so a force that is proportional to the surface area, the cell area. So it's a very simple. It's an undergrad problem. Well, actually, you have the solution in two slides. So this is the first slide, and this is the second slide. So if for simplicity, you can have a force only at the end. So anywhere the torque is the force times the distance, and this torque, the curvature anywhere is proportional to the torque. This is the constitutive relation of an elastic beam, and you have a moment of inertia here. And the stress is maximum when you have bending at the periphery, when you are away from the middle axis. And so it's simply the curvature times the Young's modulus times the distance from the axis. So what you want, or what I want at least, is to have this same constant for any given wind. And when you do that, simple math, you end up with an exponent which is 3d divided by d plus 1. So when the fractal dimension is 2, the Leonardo exponent is 2. When the fractal dimension is 3, the exponent is 9/4. Slightly above 2.
Sorry, just to recap, your D fractal dimension is the geometry.
It's
That's the number of
yes.
branches.
So it doesn't depend on the number of branches.
And the delta is the thickness, the mechanical.
Yes, exactly. And 2 is the observation of Leonardo da Vinci. So here with a very simple model, you find something very close to 2 to have, again, a constant stress in the structure for a given wind.
So if it was Leonardo's 2, which end has got the biggest stress, the periphery?
None. The stress is the same everywhere.
No. It's only if it's equal to 3 delta 1 delta plus
If you take 2
If you take 2,
and a dimension of 3, which way does it go? Yeah, you then the trunk is too weak.
the trunk is the weakest point.
Yeah, because when Leonardo exponent gets larger, the ratio between two successive ranks is closer to each other. It's like arteries. It doesn't get thinner and thinner as in a tree. So if you are, if the dimension is 2 and the exponent is, if the fractal dimension is 3 but the Leonardo exponent is 2, then the stress is the smallest at the trunk.
Smallest of the trunk.
Yeah, so you
Okay,
correct
so
the
the
trunk
trunk's
before,
large.
so this is not good. No, sorry, the stress is larger. Sorry. That's over. Your trunk is too weak. But this is this is it for a very simple model. So and that doesn't tell you in any way how it grows into a self-similar structure in the first place.
You're assuming that the direction of the wind is rather random, no prevailing.
No, yeah, it was. There's not even a direction in this calculation.
And so there you're just loading it on the end.
Yeah, just as a load like this. It's very, very, very simple.
Oh, wow. Does it change if you load it differently?
Good question. Probably. What is interesting is that when you look at a tree like this, and when you have a fractal dimension between 2 and 3, and an exponent between 2 and 3 or so, I think, then the diameters of the final branch is such that the cell area is dominated by the very small branches. When you look at this tree, actually the force is mainly at the extremity.
Depends on the length of the branch as well as the diameter.
It depends on both the length and the diameters, but if you take realistic intervals, then you always have a cell area that is larger for the extremity than for the main branches, which is completely opposite for the weight. For the weight, most of the weight is given by these branches, the branches that are below, but the cell area is the opposite. It's dominated by what's happening near the leaves. So actually considering a force only on the leaves, or considering a force in winter, for instance, when there's only the small branches, it's more or less the same. You always have a load that is mainly at the extremity when you look at this picture. So it's not completely stupid to take a force that is at the extremity. Okay, so if you're not convinced, maybe apparently some of you are not, and I wasn't completely satisfied by this model because it was assuming a fractal structure in the first place. So the question is, how do you end up having something that is self-similar? So to do that, so we built a model of growth, and we're missing some information. But, so you have a tree that is constructed as an assembly of cylinders. All of these cylinders has the same length, and the diameter can vary. It can increase. It's like wood. So you add annual wings. And so there are ramifications, but for the branches that have no children, you assume that you end this branch with an assembly of leaves that form a spherical foliage with a certain transparency. And this foliage intercepts sunlight, produce biomass through photosynthesis, and this biomass will be allocated to create new branches or to vary the diameter of existing branches. And on top of that, you have a reserve of biomass. So you can imagine that during the winter, the tree stocks some biomass that is useful in spring to build new leaves, because this time there is no photosynthesis. And this reserve will also be useful to create a seed, and you'll see in a minute what they are for. So in this structure, I can calculate for a given wind. In the linear approximation, I can calculate through simple beam theory what is the level of bending stress in the structure. And I'm assuming that every branch feels this stress and feels when this wind is, let's say, average. There's an average wind every month or every day, and each branch feels the level of stress. And I'm assuming that this level of stress is transformed into a certain request to increase its volume. So each branch feels a certain level of stress and will request to the rest of the tree some volume to increase its diameter. And so it will be requested to the leaves that are below in the hierarchy. And as the structure grows, so there are two mechanisms. One mechanism is adding new branches. So you take biomass from the reserve and you add new segments. I'll tell you in a minute what are the rules. This is called primary growth. And there is secondary growth. And during secondary growth, foliages distribute the biomass to the branches that are below, such that their diameter increase, and they distribute this biomass in proportion to the volume that was requested. And if there is any leftover, it ends up in the reserve.
Is that how it works in trees?
Yes.
Oh,
Sometimes.
Sugar transport and all that. I don't know how. Is that locally the leaves gives the nutrients to the branches nearby? Or do
So
they have to be
this mode of transport
Uh-huh.
is called autonomy. It's autonomous because you don't distribute to your cousin, you distribute only to your ascendants.
Ascendants.
So the child distributes to its mother and grandmother and so on, but you don't distribute to cousins. So that happens in some periods of the year, but not always. This is true in I think it's true in spring or in summer, I don't remember. There are very, very clever experiments where they trace the products of photosynthesis. So actually they put CO2 with carbon 13 or carbon 14, and they follow them in the tree, so they can follow for a given leaf where the sugars are going. And so they can, so there are plenty of work on this. So it's a very, very simplified way of modeling that. And every year there's a storm. So again, I'm taking a wind, but this time it's a rare event, so it's the biggest storm of the year. So I'm taking a probability of a rare event with the exponential decaying probability. And if the stress is over a certain threshold, then the branch is shed. Okay, so in this model, there are some certain parameters that I didn't tell you about. One of these parameters are when there is a parent branch and you want to add two children, how do you add them? What angles and so on? So here you can parameterize this with 3 angles. Theta 1 and theta 2 being the angles of the children compared to the parent, and gamma is a third angle that tells you how you get out of this plane, basically. So these are 3 parameters, and you don't know them. But there are also other parameters that are hidden in what I've been saying. The first one is that I told you that every branch can sense a certain stress and respond to that stress by requesting a certain volume. It's a thigmomorphogenesis. But I didn't tell you anything about the function that relates this stress to this volume, and we don't know it. It's the same for the reserve. I told you you can build new seeds or new branches from the reserve, but I didn't tell you how many and where you put them and so on. And so you don't know all these things. And one way to model that, so it's one way to model the sort of regulation of growth, or the strategy of growth, is to model these functions through formal neural networks, not because there are neurons in trees, but because it's a way to model nonlinear functions. So it's, in some sense, it's a way to model the biochemical regulatory network of all these things in a simple way. So you have, for every branch, you have some network like this with some inputs, one input being the stress that is felt, and there is some outputs. For branch, for instance, it's the volume that is requested. And the weight of these links, the synaptic weight of this neural network, will tell you the strategy of the nature of the function. And so when you do that, you end up with a certain number of parameters, and you can think of them as genes. So some of the genes are the branching angle, some others are the synaptic weight of your neural network, and altogether they determine the strategy of growth. So in some sense, for a given set of genes, it defines a species. And so the question is, and there are some non-coding genes here, and you'll see what they are for. It's for aesthetic purposes, so it gives a color to the tree. There's a red, green, blue genes. So it's like the eye color, if you want. And so the question is, what is the best set of genes, or what is the best genome, what is the best species, what is the best strategy to grow? And of course, it's difficult to formulate mathematically, but one way to not solve it, but to simulate what's happening in nature is to simulate evolution. So we take an island, so it's a circle, and at the beginning of the simulation, I'm seeding trees with random genomes. And I let it compete, and they compete for light. So each leaf produces photosynthesis in proportion to the light received, and the leaves shadow each other. So a tree will try to overshadow the others, but if they grow too fast, then they will be weak, and when there will be a storm, they will fall down. So there's a trade-off. So let's see what it looks like. So if you wait long enough, you'll end up, you start with 10 or 20,000 different species, and you end up having very few species after a while.
Is it an island or is it a planet?
No, it's an island.
So it's
A small island.
So they're growing up.
Yeah, they're growing up. We don't
In
see
the-
it,
out
but
of the-
I grow like this, and the circle is center around the leaves, center of mass, and the radius is the standardization.
And the
Color
sun-
is species?
Color is species. So color is coded through the genes that are useless for the rest.
And the sun is turning, is moving.
The sun, it's by sun. It's like Cambridge. There is no direct sun. It's a diffuse light. So the light comes from the hemisphere.
Are some of them growing in the water?
These ones are growing. The trunk is here, but since you see its center around the center of gravity of this, it means that the trunk is going outside. But these here, the seeds are produced here, so most of the seeds fall into the sea. Okay, so when you wait long enough, you end up with only one species.
Do they all experience the same wind speed, or is there a sheltering?
No, there is no shelter.
So
It's
the
an
wind is the
interesting
same
thing.
everywhere.
Yeah, this is one thing we would like to do, but it's not that easy. But yeah, yeah.
But you've coded for the fact that they're transparent, so you calculate rays hitting every foliage.
Yeah, it's a ray tracing algorithm for. Yeah. We could do the same for the wind. We could do some sort of ray tracing of wind with conservation of momentum in some sense. But I didn't do it. Okay, so you do that for 64 forest, or is it 43? No, it's 32 here. So we do it, and then it's a tournament. So it's like a tennis tournament. You end up with only one island each time. So here seeds are randomly taken. The genomes are completely random. But when I do this, I'm taking the genomes of these two islands to seed this new island and so on. What is interesting is that in the end, you have an island with two species, and the two species remain forever. So you can simulate that through 1 million years, and you have a species that is living in the interior of the island, and one species that is living at the periphery. But again, there is no sheltering, so there seems to be two ecological niche in some sense. But it's very difficult to. I don't have any explanation. It's just a fact. So that's happening, but this tree don't experience a different wind. Everything's the same, except that they are on the periphery. So these trees have more light, but they have to grow sideways. Okay, so now let's look at the forest. So what is simulated is this indeed. So it's the trees are growing vertically. So it's here. We don't see it very well, but you see at least this one. It's a smaller forest. So when you have a smaller forest, you don't have two species. You only have the periphery species that dominates. So here is this periphery species growing in a small forest, and you see the life of a tree. So it grows like that. Sometimes branches are shed by a big storm. And at first it was very small and it didn't have many resources, but in the end it overshadows all the other trees, and so it's happy, but then it dies. So let's look at the characteristics of this tree. So here with color that are more.
But this is one numerical experiment, or
Yes. Which one?
what you're showing us? I just don't know.
This
It's some
one?
kind of average. Yeah.
It's one example of. I did all these tournaments to identify the best species in some sense, the more
Okay.
adapted species.
All right.
And now I'm looking at
Single
what these
individual.
species look like. So I'm taking an island, a smaller one because what takes time is not to do the simulation, is to do the movies. So here the movie is made on a smaller island. But for now I'm going to look at one individual of this adapted species, and I'm going to look at its characteristic and its self-similar characteristics. Is it self-similar, for instance?
But it's one experiment, one numerical experiment.
But it's the solution to the competition.
What do you mean? It's one.
It's
Yeah, I'm
it's
not
the
doing.
optimal
It's the natural
species,
selection.
I'm not doing.
and you're
averages.
showing us one tree, but in the background there are other trees
Yes.
Yes,
of this
Yes,
species
obviously.
going away.
it's already competed.
Here,
So-
here
so-
it's the same species. It's already the end of the simulation. So the species that are around are the same species as this one. Just a forest of a single species forest with and I'm looking at the single individual for now.
You've chosen this individual.
I took the biggest one.
But there are other ones in the background in which this one individual is competing with.
Yes, you mean what is it representative
It's
of
not
the
in
species?
isolation.
That's the question. Is it representative of the species?
No, I just want to understand why this and not any other one.
Because it's a winner of a world tournament. It's the most adapted.
But there are others, as John's saying.
No, it's the same species. So the
But they look
individual.
different.
No,
Yeah,
they're the
because
same.
plants are plastic. They with the same way of.
Okay, so you've chosen randomly one.
Yes.
No, I took the
Yeah,
biggest one.
Tallest one.
I took
biggest one.
I took the tallest one.
The prettiest one.
The fittest one.
Okay.
But
Typical illustration of science.
In your species, how many parameters? I forgot, you said that in
31.
the genetic.
31.
Huh?
31.
31,
They are not binary. 31 real numbers. So for this individual that I cherry picked, if you want, I'm looking at self-similarity. So it is self-similar because I chose it like that way. No, all of them are self-similar, but this one in particular. All of them are self-similar. You can even see it by eye. So you have a very long trunk, and you see that it's an assembly of discs, like coins, and all these cylinders that form the tree are the same length again. And so you do that. So you plot the number of branches for a given rank, the mean length, the mean diameter, the mean cross section, and all these quantities are geometric progression. So that's a signature of self-similarity, and this is true for any, not only this species, but it's true for every tall enough individual in any species. Depends how you define if it's self-similar or not, but you can always fit and you always find something similar. And what is interesting here is that these slopes, so here in this case it gives you a fractal dimension around 2.7. These slopes are such that the number of branches and the cross section vary with opposite slopes, which means that if you multiply the number of branches by the cross section, you get something that is roughly constant, which is nothing else than Leonardo's rule. And another way to check it is to take every single branching point and to compare the total cross-section of the daughters to the cross-section of the mother. So when you plot this, it should be 1 on average, and you indeed find something that's close to 1. It's very similar. There is a lot of spread of the data, but it's really similar to what has been measured on the real trees. So this is for 5 different species. It's more or less the same plot. The area ratio, yeah, it's not the same thing on the x-axis.
Similar qualitatively.
The average is the same, and there is a spread also. Here we're interested by the average, which tells you if you are far away from Leonardo's rule or not. Here the argument is to show that you recover this rule without any hydraulics, without any assumption of how the sugar are transported or how the water is transported in the tree. It's just a result, the diameters here are just a response to the wind.
And light.
If you want a very simple picture, the fractal dimension is related to competition for light. You occupy space because you want to access light, but then each diameter is set to resist the wind. So the simple picture is that the fractal dimension is related to competition for light, and the Leonardo's rule, or the diameters, are related to wind, in this case, wind resistance. And so with this simulation, we can do other things. We can look at allometries. So now we know that Darcy Thompson is the one who made that popular. So when you do mathematical modeling, allometry is nothing else than fitting data with power laws. So here, I'm taking all the forests, so the 32 forests of the first round, and I'm stopping the simulation after 3,000 years, and I'm taking every individual, and I'm plotting a different characteristic compared to the diameter of the trunk. And these quantities, so whether it's the height, the crown radius, the number of leaves, or the total volume, so depend as power law with the trunk diameter. What is interesting is that the fit of the solid lines and the dashed lines are predicted by a very simple model, and this very simple model is nothing else than the model that I've been showing first, where you assume that the fractal dimension is 2.5. You have a regular fractal tree with fractal dimension 2.5, and you have here, I put it that way, you have constant safety against wind, or said differently, the stress is constant when there is wind blowing on this structure. And you recover there is a very good agreement. And what is interesting is that when you take this very simple model with a fractal dimension 2.5 and you compare it to real allometries, so this is data where there is the mass of leaves in front of the trunk diameter, and here it's the mass of leaves compared to the mass of branches. You see that the fit of the data and the model are almost overlap. So you predict very well the allometric tendencies that are observed in real data. Even though here we are looking at not trees, we are looking at I don't know, it's even mouse or I don't know, it's a plant for sure, but it's not a tree. The mass is 10 minus 6 kilograms. So it's a very small tree. So it's surprising that it works even here. But there's a good tendency. Okay, so to show you that the geometry of the form is a response to the environment, in some sense, it's plastic. So people doing evolution distinguished adaptation to acclimatation. So acclimatation is the fact that the traits are different in a different climate or different environment, and adaptation is the fact that the genome or the phenotype is different in different settings. So here we are talking about acclimatation. So the same species that have been shown in the forest, when you let it grow alone without any competition, the shape will be slightly different. So instead of having a long trunk and a crown at the top, you have something that is more spherical. And here you can see that the growth is mainly where the branches receive the most light. This is one of the parameters of the strategy. And you also see that the fractal dimension is, I don't know if you see it, but it's not volume filling, this structure. There's a lot of void. When you look at the fractal dimension, it's 2.3 in this case. And it's also self-similar, and the characteristics are about the same as when it is in a forest. So whether it's alone or in a forest, you end up having, in the end, a similar characteristic of self-similarity, which is interesting. So the self-similarity exponent don't tell you everything about the shape, of course.
So the difference between alone and in a forest is just the light.
Yeah, the light competition.
Sheltering.
Yes. Mm-hmm.
No sheltering from the wind.
No, there's no sheltering. That's something I shall do sometime.
I don't understand. This is the same genome as the one from the tree, but if it's the same genome, why does it look the same?
Because the genome doesn't code the shape, it only codes the regulation of the shape.
Oh, that's right.
It's a simple way to say it.
Yeah, yeah.
So you
No, you explain.
you do natural selection on the regulation, but the shapes are always adapted to the environment that can be very different. And this is the other species. So far it was the periphery species, and this is the interior species. So it looks different, but the self-similar characteristics again are very similar, and again you get something that is very close to Leonardo's rule. So the shape is different, and that will be the end of the talk. The shape is different not because the strategy is very different, but because it's slightly, the structure is slightly weaker. So for the same wind event, there is more fracture for this species than for the other one. So that's the main difference between the two. So the interior species is more fragile in a sense, than the periphery species, but slightly. But for both species, and then I'll come back to your first comment, for both species, you can look at what is the response, what is the function that has been selected, and this function is very close to constant stress, even though anything else could have been selected. So it's true that big branches are slightly less fragile or more resistant to wind, but it's very subtle, it's a few percent. So it's mostly constant stress at first order. Okay, so I wanted to share with you this work. So it's a computation of growth that includes wind biomechanics and regulation of it through allocation of biomass. So there's wind and competition for light. So the main thing is that we recover most of the allometric laws that are observed in nature. And the message, as I said, is that fractal dimensions, so the way the tree occupies space is mainly due to competition for light, the fact that you want to access light. And I didn't say it, but fractal dimension changes a lot when you change the transparency of leaves. So when you take leaves that are fully opaque, you get a fractal dimension that is almost 2, which is what you expect because the leaves inside are shadowed by the leaves of the periphery. And so you have something that is close to 2. And when you, in the model, you take the transparency to be to have full transparency of the leaves on the other limit, then you get something that is volume filling, a fractal dimension that is close to 3. And for the simulation I've been showing, transparency is in between, and so you get the fractal dimension that is also in between. And the second argument is that in these simulations, at least, the diameter are set only through response to wind, and it is interesting that you recover those rules with a very simple model. Okay, and with that, I'd like to thank the people I've been working with, and there will be a paper soon, I hope, in Nature Communication on this. Thank you very much.
What do you mean soon, you hope?
No, I'm not hoping.
Okay,
It's
all right.
accepted.
Yes, questions, Devashish.
So
Sorry. Yes, there were 3 people raising hands, so we'll do 1, 2, 3. Yes.
So have you thought of including the effect of gravity?
Including what?
The effect of gravity.
No, I didn't say it, but there's no gravity. There are 2 reasons. One is because loading by gravity is not as obvious as it seems, because you load the tree and it grows at the same time. So when you add a new layer of wood, this new layer, if it's not pre-stressed, doesn't bear any load. So to know the stress inside every branch, you need the history of loading together with the history of growth. So it's not completely obvious to compute the stress due to weight. That's one of the reasons. And the other reason is that when there is only one mechanical stimulus, wind, there is only one dimensionless parameter that characterize it. And this parameter is simply it's rho u square divided by the strength, which is the stress at which the tree breaks. That's the only dimensionless parameter you need. And with this dimensionless parameter, the length you choose, for instance, the length of each cylinder is not important. It's one. It disappears from the. There's only one dimensionless parameter in the characterizing the mechanics of your structure.
Yes.
Is there any data on root systems?
Yes.
Do they satisfy Leonardo's rule?
Do they what?
Do they satisfy Leonardo's rule?
Oh, there is one paper I know of which says that it does. And for roots, obviously it's not the same argument. There is no wind. So maybe for roots, hydraulic arguments are correct. There's only one paper I know of. So there are not that many measurements. But for branches, there are like 3 papers. So it's not like we have plenty of data. It should change in the near future because now they have LiDAR. So they scan through lasers trees, entire trees. So far there are problems of reconstruction because there is only parts that are shadowed. But we could expect in the future to have plenty of data with all the lengths, geometry of very complex trees without having students measuring every single branch.
Alex?
Just out of curiosity, how expensive are your numerical routines? It sounds like it's awfully complicated, especially the modeling of light.
So it runs on this very expensive computer. And one...
It's in MATLAB, it will be in MATLAB?
No, it's not MATLAB. It's in Fortran. But the one forest like this, so 10,000 years, the movie you saw, it's, I don't know, a few hours. Actually, it's more expensive to do the movies. Doing the movie is like a week, this movie, but computing it is like 5 minutes.
Maybe this is because I'm not very smart, but I'm confused by this whole strategy that you're employing here. It's as if you're trying to recreate evolution to begin with in some simple model. Why not? I understand you want to simplify a model so you have certain number of parameters. Why not take these parameters from how trees behave?
Because we don't know.
But you just said yourself that people measure how nutrients transfer.
See the result of it, but you don't see the causes.
So I think there is a... Okay, I take your point. It's a good one. I started this by doing optimization. So before doing this forest and this simulated evolution, I did optimization calculation. So there was only one tree, the wind was constant, or it was always the same history, and I was trying to find the best strategy, so the best parameters, such that the tree was the tallest, the biggest volume, and so on. And it was very hard to find. It was not well posed because a very small change of parameters could change completely or a wind that is slightly different one year completely changes the picture. And somebody suggested that. And what is interesting is that when I take one of these trees that is selected after, even after 10,000 years, and I make it compete with a tree that is optimal for size or for the number of seeds that are produced or whatever you choose, it's completely, the one you selected through optimization, you lose the competition all the time. So it's important to have neighbors and to have, so maybe it's not satisfying from a mathematical point of view because you're not optimizing something. But what is interesting here is that what resembles the real evolution is that what you select is not the best strategy when conditions are average. You select the species that resist the storms that only happen every 10,000 or 100,000 years. in order to get here, you need to survive all the events that took place, and even the very rare ones. It's not the same as optimizing for average condition, completely different. And I don't know if it's satisfying, but you're not optimizing anything here. You're just running something that looks like evolution, but that's the only thing you can do. And that's the only thing I can think of when conditions are very different. And when you want to optimize something that is, you don't optimize the shape or something that you can calculate or you can measure on tree. You are optimizing regulation. And we don't know anything about or we know some few things, but we don't know anything quantitative about how regulation is made. Which genes, which proteins are implied, which hormones are implied when they regulate the growth. Something completely, we don't know, I mean, we don't know anything for, I don't think there is any organism where we can put on equations how growth is regulated. And this is, since we don't know it, one way to have something, at least, maybe not an answer, but to have something is to simulate evolution and see if trees that are adapted in this simulated environment share things with trees that are in nature.
Maybe it's 10 past, so let's do one last question and then let's close.
So I mean, this is probably more a comment than a question. So I understand, so let's assume all these things you have done, are sensible, and you basically sort of come up with some prediction of some, real life tree, how they more or less look like over many years of, reaching some kind of steady state. And but there are different scenarios, right? For example, if you apply your system to some invasive species, some plants and stuff, it'll be very different, right? You don't really need to rely on them reaching some equilibrium. You're just simulating the spread like crazy. So it'll be a very different outcome, perhaps.
Yeah, that's something that was also suggested. So for plants, there are pioneer species.
Right.
So when there is a fire or when there's something special like this, some species are the first to the pioneers. So they colonize the space, but so they grow very fast and usually they die very young, and eventually they'll be outcompeted by others. So I don't know the name in English, but there are several species of trees like this. In this scenario, it cannot happen because there is no such thing as a fire or something like this. But we could, I mean, this, I'm not saying that, I'm not expecting to find every single species of tree. Actually, I was expecting only one species with this tournament. It doesn't explain anything about the biodiversity and so on. But yeah, it would be interesting to, if you change the way competition is run, if you could have competition for very short times, for instance, and if you do that, then pioneer species would be favored, and probably you'll have something very different in the end. So of course, the result of you find in the end depends on the condition of the competition. But it's also true in nature. And also there is only one resource, light. There is no nutrients, there is no water, there is no parasite, there is no insect, there is no, and so on. So if you add everything, there's just wind and light.
So I see that every time we have a talk about evolution, it stirs up a lot of emotion, which is, I think, a very good thing. I would like for us to thank Christophe once more.